Good evening, ladies and gentlemen. Welcome to the Walter and Eliza Hall Institute of Medical Research, WEHI, and to this public lecture. The 11th in this series, a Science Meets Society series. And the title this evening is As Malaria, a Global Disease, Can It Be Eradicated? And the event coincides with World Malaria Day 2013. My name is Graham Mitchell, formerly of WEHI and a current board member, standing in for Alan Cowman, the head of the large and flourishing malaria program here at WEHI. And Alan wants me to express his apologies for not being here at the moment. I think he's in flight from Singapore as we speak. Firstly, on your behalf, I'd like to acknowledge the traditional custodians of the land on which we meet, the Wurundjeri people, and we pay our respects to the elders, past and present, of the Kulin Nation, and certainly extend that respect to other Indigenous Australians present tonight. As I mentioned, currently WEHI has a very productive malaria program, and I know actually when it started. It was 1977, following a conversation I had with the then director of the Papua New Guinea Institute of Medical Research, Michael Alpers. Now, Graham Brown will remember this date because Graham Brown and Robin Anders were the first two star recruits into the malaria program, 1977, 35 years ago. The program has always had a focus on a deeper understanding of the immunology and molecular biology of malaria, primarily falciparum malaria, and we'll hear about the different malarias this evening, with a view to rational vaccine design. Seeking the Achilles heel of the parasite and attacking it at its weakest point, the soft underbelly, if you will, if it has one, these malaria parasites, attacking it through its weakest point. And we're going to hear some very exciting things tonight in this long journey to conquer one of our greatest scourges. And as we'll hear, malaria parasite is a formidable adversary with many tricks to thwart our earnest endeavours. And this is not an endeavour for the dilettante or the faint-hearted or the sprinter. It's a race for the stayers. It's going to be long and difficult, but we're going to hear tonight about what progress has been made in these last couple of decades and accelerating pace of advances in this field. A couple of housekeeping matters. You will have noticed the exits, and I'm sure if there's an evacuation noise down the stairs out onto the Oval. The event is being live streamed and filmed. Keep that in mind, all the questions and whatnot, and will be available on the WEHI website. Can I ask you to check that mobile phones, including amongst our speakers, it's very embarrassing to be giving a talk and the mobile phone goes off, they're turned to silent or indeed off. Now, let me introduce all of the four speakers and the panel, their panel members up front, so as not to impede the flow of the presentations, because you'll see they're all very linked, and it'd be nice to have that flow rather than a 2 or 3 minute interruption with me introducing. So let me start with the in order of appearance. Professor Louis Schofield is a Principal Research Fellow here at WEHI. Louis undertook PhD studies at the Queensland Institute of Medical Research and was a postdoctoral fellow at New York University and the National Institute of Medical Research in London. He has been a key member of the malaria team here at WEHI for many years now, but he's also the Director of the Queensland Tropical Health Alliance and Director of the Australian Institute of Tropical Health and Medicine. His research is aimed at developing malaria vaccines and has been funded by the Bill and Melinda Gates Foundation, the Howard Hughes Medical Institute, the Australian and US governments, the European Union, the World Health Organization, and various industry partners. Now, Louis' title this evening is Can Vaccines Contribute to the Malaria Eradication Agenda? Our second speaker is Dr. Wai Hong Tham. She's a laboratory head at WEHI, and her research focuses on how malaria parasites enter red blood cells. It is anticipated that a deeper understanding of this key biological process will lead to new control measures, including vaccines. Wai Hong undertook PhD and postdoctoral training in the US, and coming to Australia, she was awarded an Australian postdoctoral fellowship and an Australian Research Council Future Fellowship. Together with her colleagues at WEHI, her work on malaria parasites was awarded the inaugural Eureka Prize in the category Infectious Diseases. And Wai Hong's title is How Malaria Parasites Enter Red Blood Cells. Our third speaker, Professor Ivo Müller, hails originally from Switzerland, but after 16 years research experience in Papua New Guinea and the Asia-Pacific region, he can rightly claim to be the preeminent malaria epidemiologist in the Southwest Pacific. His research centres on field-based studies of malaria, treatment and prevention, and the slow acquisition of immunity in people living in endemic areas. He has a particular interest in Plasmodium vivax, probably the number 2 malaria parasite after Plasmodium falciparum, or falciparum. And Ivo's title is Malaria Elimination in the Southwest Pacific, Is It Feasible? And a very particular pleasure to introduce my close colleague, Professor Graham Brown. Graham is the Foundation Director of the Nossel Institute for Global Health at the University of Melbourne. He has worked in Tanzania and Papua New Guinea, and as I mentioned, was a foundation member of the WEHI malaria program in the late 1970s. Graham has deep clinical expertise in infectious disease and tropical medicine, and was head of the Department of Medicine at the University of Melbourne from 1999 to 2007. His research interests include the pathology of malaria, including during pregnancy, a critical endeavour, antigenic variation in the parasite, how these parasites keep one step ahead of the immune system by changing their spots on their coat, disease surveillance, and the use of low-cost technology in health, including malaria. He has served on numerous international committees, including the Bill and Melinda Gates Children's Vaccine Program, the World Health Organization Tropical Disease Program, and the USAID Malaria Vaccine Development Program. In 2010, he was made a member of the Order of Australia for services to medicine in the field of infectious diseases. And the title of Graham's talk is exactly the theme tonight: Malaria, a global disease, can it be eradicated? So, ladies and gentlemen, that's a brief helicopter view, if you like, a brief introduction of the credentials of our 4 speakers and our panel members this evening. Highly credentialed, you will agree. And those bios illustrate, I think, in terms of the training and the involvement and the funding, what a global endeavour this really is, and in which they are involved. So the format is that we'll have the 4 presentations. Louis will have a little bit longer because he's going to show some video clips and things. Then a Q&A session involving all of us, and which I will moderate. Eat your heart out, Tony Jones. And then, of course, we will conclude, as the program indicates, at 7:15, and we'll adjourn for refreshments outside the theatre. So without further ado, ladies and gentlemen, a hearty welcome to everyone. Looking forward to a fabulous evening, a great dialogue, not a series of monologues, a dialogue where we all get involved. And it's my great pleasure to introduce the speaker, number 1, Professor Louis Schofield. Louis.
Well, thanks, Graham, for that very enthusiastic and ebullient general intro. So, as Graham said, the title of my talk is "Can Vaccines Contribute to the Malaria Eradication Agenda?" It's an interesting and important question. So, I want to start off by just, I've been in malaria research for about 30 years, and for most of that time, this is the global picture that's prevailed. We've had a situation where about 40% of the global population is at risk of malaria at any given time. There have been 300 to 600 million clinical cases a year, so that's 10%, between 5 and 10% of humanity gets malaria every year. And it's true that the overall, what we call the case fatality rate is low, so only 1 or somewhat less than 1% of cases will actually proceed to death. But with that burden of disease, you can see that you end up with something like, I mean, estimates vary, that numbers are very rubbery, but something like 1 to 2 million deaths per year, mostly in children and pregnant women. Now, just recently, that situation has changed, and in fact, we have a situation now where the death rate has fallen, but nonetheless, even now, in this evening session, as we give our presentations, there will be about 95 deaths globally, mainly in children. And going back a few years, that would have been even more, maybe 125. But there's been a bit of a reduction in recent years, and one of the major reasons is because of the commitment, the international funding, to apply the existing technologies and ramp them up and apply them at a higher scale. So there are, I think, 3 critical technologies that have been useful in achieving this partial rollback of malaria. First of all, the deployment worldwide on a global scale of long-lasting insecticide-treated bed nets. Obviously, bed nets will protect you if you use them, and if you cover them with insecticides, as the mosquito comes in touch with the net, it will die. So that's been a very useful tool. Also, artemisinin-based combination drug therapies. So artemisinin was a drug that's thousands of years old that the Chinese discovered traditionally in traditional medicine, but has only recently been ramped up and deployed on a global scale, and it's a very effective antimalarial drug. So together with these measures, and to some degree with rapid diagnostic tests, we've seen a partial rollback in the severity of the global burden of disease. And in fact, so much so that in 2007, Bill and Melinda Gates of Microsoft fame, through their foundation, adopted malaria eradication as their key objective. So now, you know, there are a lot of consequences that flow from announcing a plan to eradicate such an important disease from the face of the planet. It's far from trivial. So one thing that's clear is all the benefits I've just alluded to do have flowed from the application of these existing measures, such as bed nets, drugs, and diagnostics. So an important question that's raised, there has been something like 20 years or 30 years of research into malaria vaccines with not a great deal of success. So are the existing measures sufficient? Do we need new tools? And specifically, can vaccines contribute to the malaria eradication agenda? Well, good question. I'm glad to say, I mean, let me make it quite clear that when this is basically a resource allocation issue. If you're going to spend billions on antimalarial measures, how much are you going to invest in the vaccines, which are an unproven technology so far? So the academic community was scratching their heads around this and humming and hawing. I was fortunate to be invited to the panel that reviewed this issue on a global scale. And the point that was made as in our deliberations was that the eradication of smallpox and poliovirus infection globally, which has been achieved, and the elimination of polio and measles on a very large scale, was achieved using vaccines as the primary intervention tool. In fact, so far there's never been a disease that's been eradicated without use of a vaccine. So as malaria transmission diminishes, mosquito control, bed nets, new drugs that have been used will surely play critical roles. But the lessons from the viral disease programs is that vaccines that interrupt transmission should play a critical role in helping to eradicate malaria. Okay, and that came from, so that was the view of the community. There is still a role to play for vaccines, but it's an enormous challenge. And here's the best vaccine that's been developed so far. GlaxoSmithKline, what they call the RTSS vaccine. So it's cost nearly $1 billion. They've been put into very large clinical trials, and the real problem is that it only lasts, its efficacy is very, very limited. I mean, you can argue about this. Some people say it's more than 10 weeks. It might be 12 or 14 or 16, but that is nowhere near enough to get the kind of impact you'd need for the vaccine to be effective on a global scale. So then there will be a role for this vaccine will be licensed, but there's certainly far more needs to be done. And the real problem is, as I'm going to show in this slide, some of you may have seen this presentation, but and I apologize, you're going to have to sit through it twice, but I believe a lot of people have not yet seen it. So this is an illustration, a movie that was made here at WEHI using computer graphics by Drew Berry, and illustrates one of the key issues in the malaria, the complexity of the malaria biology, the complexity of its life cycle. So, oops. It's, The link's not working, guys. There we go.
The malaria parasite is an ancient organism. It has been with us since before we were human. Famous victims include Alexander the Great, Genghis Khan, and George Washington. The malaria life cycle follows a devious path, swapping back and forth between mosquitoes and humans. This mosquito is infected with the malaria parasite. Because she is pregnant, she has become hungry for human blood. During the bite, she injects saliva to stop the blood from clotting. Her infected saliva also carries the malaria parasite. The parasite rides the bloodstream like a network of roads, seeking its first target, the core of your body's blood filter system, the liver. Sensing its arrival at the liver, the parasite searches for an exit. A sentinel Kupfer cell is the entry point to liver tissue. Leaving the blood, the parasite infects a liver cell, killing one or more other cells on its way. Over the next few days, the parasite undergoes hundreds of nuclear divisions, copying its DNA over and over again. A single infected liver cell can create thousands of new parasites. The next generation of parasites are modified to infect a new target: red blood cells. Inside a red blood cell, the parasite can hide from the body's immune system. The parasite slowly devours the contents of the infected cell and creates more parasites. The infected cell becomes sticky and grips onto blood vessel walls. Once mature, the infected cell bursts, spreading more parasites through the bloodstream. Malaria victims suffer fever, loss of blood, convulsions, brain damage, and coma. This year, 10% of people on Earth will be struck down with malaria. Countless millions have been killed by it. Most people who die from the disease are pregnant women and children under the age of 5.
There we go. Now, the point about the take-home message I want you to take from that video was essentially the complexity of the parasite's life cycle, and that's shown in schematic form here. And this presents the single biggest challenge we have to developing a vaccine, because every single form is quite different. It expresses completely different proteins on the surface, changes the cell morphology, the organization, has different strategies. And any single vaccine that the people have been trying to develop so far has necessarily focused on one or other stage, and essentially you miss the picture of trying to hit the organism across its whole biology. So the vaccine I alluded to, GlaxoSmithKline's not very effective RTSS vaccine, tries to hit the sporozoite stage, but does nothing to control the replication of an infection in the host and certainly does nothing to prevent the transmission to the mosquito, so the cycle can keep going. So this group of experts that got together and said, well, do we need a vaccine? Said yes, it would be desirable, but what we need to do is we should be aiming to build a vaccine in which the ideal vaccine target would be invariant, not changing its spots the whole time, which a lot of the proteins do on the surface of this parasite. It would be highly conserved across all malaria species. Don't forget there are 5 species, 5 completely different strains of malaria, 5 completely different species, all of them completely different to each other, expressed on the surface of all differentiated life stages, the sporozoic stage, the liver stage, the blood stage, and the mosquito stage. It should provide clinical protection and induce transmission blocking, meaning you can't transmit it from the human host to the mosquito. And the reason I put an exclamation mark after that is because that's almost an impossible task using at least current thinking. Well, as it turns out, we believe we've identified exactly such a target. When I'm going to tell the rest of so far this has been an introduction to just a little bit of actual recent data, which I'm going to show you from my lab, in which we think we've got a molecule which fulfills all those criteria. So, and once again, it's a typical left field sort of thing. We were working on an area that we didn't expect and found this. We were working on this molecule, which occurs in the parasite. It's got an incredible name, a glycosyl phosphatinositol, which is 28 letters. We call it GPI for short. Okay, for obvious reasons, okay? And the GPI is not a protein, it's a glycolipid. It's made of sugar and lipid, all stuck together. And the thing about this molecule is that when we isolated it from the parasite and shoved it into mice, basically they died of a disease that looked a lot like malaria. It gave them a really severe fever, it gave them problems and severe inflammation, and we believe that what we'd identified was a toxin of parasite origin, which when released into the blood causes the disease symptoms. And we had the idea, well, that's great. You could vaccinate against the toxin and induce an immune response against the toxin. You might at least provide clinical protection against the disease. And in early vaccine trials, that's exactly what we found. We had a mouse model of malaria, and normally when you give them malaria, they die with a fulminant disease looking like very severe malaria, full of inflammatory processes and fever and such like. When you vaccinate them using the sugar head group of this molecule, the animals are completely protected, or not completely, but substantially protected. So this is the survival, and after 6 days, the control group all die, but when they're vaccinated, about 75% protection. And when you look in the brain, you do histological studies in the brain, you see that these animals that have disease are from this group, and their blood vessels in their brain are all jammed up and sticky and occluded with parasites, whereas vaccinated animals have free and clear blood vessels. So we really thought that this is an important toxin that would be responsible for disease, and vaccinating it would be a great strategy. But despite this is not sufficient to meet those criteria that you can vaccinate against the toxin, prevent disease, but you're not going to block transmission, or so it would appear. But in more recent studies, we found, quite surprisingly, that that's actually not the case, and that the toxin is expressed all over the surface of this invasive form here, and is somehow involved in this invasion process, as shown by yet another of these movies. So they're the parasites getting in, and as I'll show you very briefly in the last few minutes of my talk, by vaccinating against the toxin that's on the surface there, we can, in fact, get some prevention of this event. So this is a cartoon demonstration of that, and the toxin is expressed all over the surface of the parasite here, and is part of this fluffy coat. And as it goes in, if you vaccinate against it and you have antibodies there, that process is inhibited. So this shows is a picture of that. These are real data, only generated quite recently. The green picture shows here's the parasite bumping into the red cell here, and you can see it all over the surface. And as the parasite starts to invade, it's left behind as it moves into the red cell, the green toxins all over left at the surface there, and as it's nearly in, you can see just a little bit left behind there, and as it goes in, it's all shed. So this tells us that the toxin is somehow intimately involved in this process of getting in, and if you attack it, you will not only prevent disease, but you somehow prevent the parasite from getting into the red cell. And we see that in vaccination models. The animals have very low parasite burden. That's not all. Remember, there are 5 species of human malaria. This toxin is identical in all 5 species. And not only that, it's in the blood stages, but as shown here, the toxins on the surface of all the other different stages that are in the parasite. So this is the sporozoite stage, and these are the sexual stages, okay? And in our recent experiments, a student in my lab, Steph Tan, who's listening outside, Stephanie Tan has done experiments of this type to show that if you vaccinate mice against the toxin that prevents the disease, and you go and feed mosquitoes on those mice, actually the mosquitoes have a reduced malaria burden, as shown here. So somehow antibodies against the toxin is also preventing the transmission from the human host to the mosquito. So that's really exciting new data. It's very preliminary. Actually, this needs to be reproduced. This is not publication quality data, so don't all run around and tell everybody that this is firm and solid. I'm just giving you something up to date. But let's hope it's reproducible, because that would make a big difference. So in summary then, for this particular kind of approach, we has developed an intellectual property position around this. We started a biotech company around this idea. We've got about $30 million of development funding to date. We've pioneered a low-cost synthetic pathway to try and make this molecule cheaply. And we've developed a relationship with Merck Incorporated in the United States. They're a big vaccine manufacturer, and they have managed to develop formulation processes, which means, find a way to sort of package it so it could go into humans. And it's very effective in what we call the preclinical trials, and it targets all life stages and all species of malaria. So that's the to date. And the point is now, I believe, that we're in a position to take this candidate forward to phase 1 and 2A safety, immunogenicity, and efficacy trials, okay? And I'm pretty happy for you to leave it at that point. So thanks very much, Graham.
Thank you, Louis, and for showing Drew's videos as well. Now, you saw a parasite entering a red cell. Wai Hong is now going to tell us a little bit more about that process. Wai Hong.
Hi, so my name is Wai Hong, and I work here at the Walter Eliza Hall Institute. And what I was interested in is how malaria parasites actually enter into human red blood cells. Sorry, they're just loading up the presentation. There we go. Here we go. So what I'm interested in is really what Louis showed you before, is you see these parasites and how do they get into your blood. And what this cartoon here shows you is basically a malaria parasite, and I'll refer to this form of the malaria parasite. It's called the merozoite. And all the merozoite does is that it's the form of the malaria parasite that can get into your blood. So the reason why we want to study this is to understand how we can block this process. But another really fascinating part of this part of the life cycle is that this form of the malaria parasite is completely exposed to the human immune system, which means that we can train the immune system to attack this form of the parasite through vaccination or perhaps through drug treatment. So this becomes a really great point of intervention that we can develop through science and understanding of how this process happens. So here, what we have here is basically red blood cells, which you can't even see the outside of. But here you have a red blood cell that's packed with purple dots. Each one of these purple dots is a malaria parasite. It has been growing in this red blood cell for about 48 hours, and it's set in there. It's basically eaten up all the protein that's present in the red blood cell, and now it's done with it. It wants to come out, it wants to rupture out, and it wants to find other healthy red blood cells. And this is how devastating this part of the life cycle is, which is really responsible for all the clinical symptoms in malaria infection. So here you see all individual ones of these merozoites will rupture, and each single one of these become an invasion machine that will get into your blood and start the whole 48-hour cycle of consumption and then rupturing out to invade more red blood cells. So here's one of these movies. We love them so much because they're so science-based. And what I want to see is that the merozoite has actually reorientated and actually propels itself straight into the blood. And a lot of the science that we do here at WEHI is to really understand how these processes happen. And although these movies don't show them, these processes are happening in a very short period of time, in tens of seconds. And we try to take apart what's occurring during that time. And through lots of work in the lab, we can also see visually how these processes occur. Here's just a cartoon diagram. This is the malaria parasite, and it has its apical tip to the red blood cell. And I'll come back to this stage of the malaria parasite because this is the stage where the parasite has actually found the red blood cell and it's decided to commit to entry. And this is the stage where we really try to block a lot of the processes. Here, the parasite has committed, and then it activates processes that will push it into the red blood cell. And we can see this brilliantly through labeling either the red blood cells. What you see here in blue is basically the parasite nucleus. And what you see here in green is labeling one of these parasite proteins that are completely crucial in parasite invasion. So you can see in the lab, we can actually monitor how all of these parasites are going in. So the malaria parasite that none of these movies really show you in real life is that it's really only 1 micron in diameter. That is 1 in a millionth of a meter. And if you just strip that back, and we've stripped basically and let you have sort of an inside view of what this parasite looks like, and it is incredible. It has beautiful specialized structures that make this basically an invasion machine. And what I want to show you in the next few slides is to just take a couple of these structures and tell you how it actually functions in parasite entry into red blood cells. So the first one of this, which Louis sort of alluded to, is basically the surface coat. And the surface coat is what you see here on the outside of the malaria parasite. And it's shown here as the gray carpet. And what the gray carpet here is really a diagram of lots and lots of parasite proteins that sit here. And they basically form Velcro. And they kind of Velcro onto basically red blood cell membranes. So what you see here is a malaria parasite and a scanning EM image. And the fuzz that you see all around it is basically the surface coat. And they have an ability to bind and find red blood cells. And what's really intriguing about these proteins is that they're also completely exposed to the immune system. And one of the really active areas of research is understanding how parasite proteins, which are completely exposed, interact with the human immune system and how we can actually use that as points of intervention. The second set of organelles that are present in the parasites are present at what we call the apical end. So you can see that the malaria parasite is oval, and there's definitely a cone-shaped protrusion. And here at the apical end are 2 types of organelles. First are the micronemes, and the second are these funny little pear-shaped things called the ruptries. And they contain lots and lots of proteins. And at the point where we've talked about where the malaria parasite commits to entry, where the point of the malaria parasite actually interacts with the red blood cell, what the malaria parasite is doing is putting a lot of these proteins that are present here at the apical tip. And what these proteins do is they seek very specific red blood cell proteins that are present. And what that tells the malaria parasite is that I've found you, you are a red blood cell, I know I can grow in you, and I know I can enter you. And this resembles the point of commitment. And this is actually what we study here in our lab at WeHi, is to understand all these partner interactions between parasite proteins and red blood cells. The other thing that these apical organelles do, micronemes and ruptries, is that they're full of fat. So the parasite wants to enter your red blood cells and set up a home. Normally what we do in renovations is to basically paint our house. What parasites love to do is to shoot in globules of fat. And what that does is to set up membranes where the parasite can actually stay in. So here you see a malaria parasite. Apical end is touching the red blood cell. It is committed. It knows it can enter. And the first thing it does is to send in proteins and lipids. And here you can see globules of lipids that come in. So not only has it attached, it's actually putting things into your blood that's going to set up its new home. And the last structure that I would like to talk about is basically the parasite motor. This is really something that's very hard to see. And really, this is the reason why we have a cartoon of these motors. These motors sit actually underneath the membranes here in yellow. And what you can see here is a malaria parasite here here, and it's getting pushed into the red blood cell. And at points of contact, which are labeled with TJ, it's called short for tight junction, this is where this motor exists. And this motor is actively pushing the malaria parasite straight into your blood. And all this is happening in this organism, this pathogen that's only 1 micron in size. So what I want to do to end with is to sort of give you a flavor of why we do this. So one of the big parts of parasite entry that I study is basically when the parasite commits. And what we try to understand is to understand that biology so that we can develop inhibitors to block parasite entry. So what we're going to see is you're going to see live parasites getting into your blood. And before I start the movie, I want you to focus on this over here. The moment I start the movie, all these parasites, 30-something of the parasites are going to explode out and they're going to rupture into your bloodstream. And what I want you to notice is that when it encounters another healthy red blood cell, it actually causes very active change. Parasite exit, you see? The contact with the red blood cell, these are these active processes that we're talking about that's happening. If you missed it, here's, oops. Sorry, I'll start it again. There's another one that's going to attach over here. At some point, you see that, and then in it goes. If you miss that, in that goes. All right? And all this is happening under a minute from rupture. This is how fast parasite invasion occurs. And within a minute and a half, you see that red blood cells are actually undergoing change. And this is what happens when parasites can enter. So what we've done in the lab is to understand this process so intimately that we can actually develop something that blocks this process. So here you want to focus on this infected blood. It's going to rupture out. And then I want you to see what's happening when it contacts other blood. You get rupture, parasites come out, they swim around, but you never see any of these active processes that are happening. They may swim around other red blood cells and push them around, but here's one that's skimming right on top, and nothing active is happening. And the reason why this is occurring is that it doesn't recognize that it's sitting right on top of a red blood cell, because we have blocked that point in time of commitment of the parasite entry. And so what we hope to do through our research in the lab, and malaria research is wonderfully multifaceted. There's the humans, infected cells, the mosquito host, immune cells. And what we study is in the parasite, and what we hope is that through our understanding through science, we can actually reduce the burden of this devastating disease. Thank you.
Thank you, Wei Hong, a beautiful illustration. We now move from the lab to the field, and Ivo will take on the topic of a malaria elimination in the Southwest Pacific. Is it feasible? Ivo Müller.
Thank you very much, Graham. So after the world of microns and beautiful biology and interaction between molecules, I want to take you to a much bigger scale, out to the field and into the scale of what happens in our region in terms of malaria. And talking about malaria elimination in the Southwest Pacific and whether it's feasible. And I would like to remind you that Australia had malaria, and I think only in 1972, Australia was officially declared malaria-free by WHO. And if I remember correctly, the last major outbreak of malaria in Australia was in Darwin in the late 1950s, where there was around 100 cases or so of malaria locally acquired. We also still have the mosquitoes here because we just recently had a couple of cases in Cairns when somebody came from overseas, probably from Papua New Guinea, was infected with parasite, mosquitoes were biting the person, and 3 people in Cairns who never left Cairns got malaria in Cairns. So that already answers the questions. Yes, we have eliminated malaria at least from one country in the Southwest Pacific, and that's Australia. So I think before we're talking about malaria elimination, it's very important in eradication that we get clear what we're talking about. And we're talking about eradication, elimination, control, and all these terms. And it's very important we understand the target before we are looking at before we are trying to hit it. What do we mean with control? With control, we mean we want to reduce the number of people that get sick and die from malaria to the point where we no longer really consider this a major public health problem. Elimination means we interrupt transmission of the parasite from one person to the other, and we have no clinical cases in a defined geographical area. That can be an island, that can be a country, that can be a continent. Eradication means we've killed off the last parasite out there in the world. We no longer have any transmission anywhere in the world, and we have no longer any parasites and cases of malaria anywhere worldwide. Now, this is obviously our end goal, but this is an extremely difficult target to hit. This is a much more feasible target to hit. So the question I'm asking is elimination possible from our part of the world, the Southwest Pacific? So to start this, we have to see where is malaria now. And these are two maps that were produced by the Malaria Atlas project. The citations here has gone missing. That show where we still have malaria now in terms of Plasmodium falciparum and Plasmodium vivax. And the first thing you noticed that Plasmodium falciparum really is now being pushed back to its tropical heartland from Vanuatu through Solomon Islands, Indonesia, the Southeast Asian countries into India. But in the kind of more temperate areas, Plasmodium falciparum has already disappeared. Plasmodium vivax, on the other hand, is still found in Korea, it's found in central China, and it really has a much broader distribution through the Asia Pacific. So these parasites, which I spend a lot of time studying, is really the predominant parasites in our part of the world, while falciparum kills many more people because it's so prevalent in Africa. This is our main foe here in the Asia Pacific. And as it happens, it's also a more difficult foe in terms of being able to eliminate it, because it can hide inside our livers for up to 2 or 3 years, and they wait there for drug treatment and evade the immune system by just sitting there, and then when it thinks the air is clear, it will come out again and will cause another infection. So in terms of elimination, that's the current picture today, where we have a number of countries that are malaria-free. Some of them have never had malaria, but we have a whole number of malaria, like Australia or the US or much of Europe, that used to have malaria 100, 200, 300 years ago, and that have now been malaria-free for the last couple of decades. We have 32 countries at the moment that had officially declared that they want to eliminate malaria, including Vanuatu and Solomon Islands here in our region. So what approaches are currently being used in these programs? These are the similar kind of approaches that Louis talked about that are used in control. So we want to have universal access to good diagnosis and treatment with an effective antimalarial, universal access to treated mosquito nets, where transmission is high and focal, some spraying, indoor spraying of houses where they get sprayed with insecticides so the mosquitoes that enter houses get killed. Also, we're using social marketing and behavioral change program to try to get people to change the way how they interact and how they live. Bed nets are no good if people don't use them. People who don't go and seek treatment when they're sick and get drugs, they keep spreading malaria. So if we do not get the people in the areas to change their behavior, the best technology is very difficult to make a difference. Also, we really need to improve the way how we monitor and evaluate. If we cannot find out where malaria, if there is little malaria left and we can't find out where it is, we can't hit it. So we need to know where it is. So this is a quick roundup of where we are with malaria here in our region. This is data from the World Malaria Report in 2012. This is Vanuatu, and you see all through Vanuatu we have some malaria, but in the north more and less in the south. We've seen a nice decrease of malaria over the last 10 years. If you take that back to 1990, it actually stops up here and has a really dramatic reduction. Since 1990, we've seen a 95% reduction of malaria in Vanuatu. We are down to a few hundred cases of malaria in a country of 250,000 people. Malaria has already been eliminated from this island here, and it is very close to elimination in this group here. When we do a survey and go and bleed people, we can't find parasites really any longer. And I think last year in this group of islands, they've had 17 malaria cases. So local elimination is clearly possible. It has already happened. And there is a clear goal by the Vanuatu authorities to reach malaria nationwide elimination by maybe 2020 to 2025. In Solomon Islands, the situation is a bit more tricky because what we have here is a real patchwork. We have some islands like this one here, or even Rennell here, which is completely malaria-free, never has had malaria in its history. And we have areas like Guadalcanal or Malaita that have very high levels of malaria, really highly endemic malaria. So yet still we have again seen a roughly 90% reduction between 1993 and 2013 in 20 years. We have extremely low malarias now on islands like here in Isabel, or this group of islands here, which is Tumotu, where the prevalence now is that less than 1% of people living there are actually infected with malaria, down from 20, 30, 40% 20 years ago. Unfortunately, in Solomon Islands, we still have really high levels of malaria in the central group of islands here, and this is the central province here, where we from WEHI have a field site and are running some large field studies to try to better understand the epidemiology of malaria transmission in the Solomon Islands. So the conclusion here for Vanuatu is probably that local elimination is possible, it's on the way, but to really eliminate it from all the country of Vanuatu, we still think it's going to be quite difficult to achieve until we really get a handle on these central islands here that keep the malaria transmission going there quite strongly. Now to Papua New Guinea, which is a bit our problem child here in terms of malaria. Firstly, we see it's full up with malaria. We have lots of dark areas here with huge amounts of malaria. When we look at the trend over the last 20 years, there is no trend. Nothing really has happened the way it looks like here. However, that's painting things a bit black because you do see a little dip here, and that dip is actually real. We've made some real progress in Papua New Guinea in the last 5 or 6 years. With funding from Global Fund, Papua New Guinea has received totally almost $100 million since 2004 for malaria control, has restarted its program, and has made big progress. And I'll show you that in more detail. But we have seen a 40 to 50% reduction in malaria burden, not the 90, 95% like in the neighboring countries. But this is very dramatic. This means thousands of children survive that would have died 5 years ago. But we have still these areas that are really high and with high burden, and therefore Papua New Guinea quite sensibly has said, we're not yet talking about elimination here. We first have to get that burden of malaria further down. But what has happened in those times? The first thing is Papua New Guinea has distributed about 2.5 million vet nets to its 7 million people. And you can see in pre-start of the program in 2007, and these are the insecticide-treated nets here, these LLIN, which means for long-lasting insecticide net, there was less than 10% of people had access. Less than 10% of households had one of these nets. In 2011, over 80% of households had at least one net. Dramatic increase. That comes to behavioral factor. People are not as good at using them as at owning them. So only about half of the people who have nets are actually using them. So if we can't change their behavior, we have this really big gap. So the program works very hard with radio spots and programs and school messages to try to lift that up. That not just 80% or more households have nets, but that really 80% of people are using the nets. But even this not so good use has already had a dramatic impact, in particularly on Plasmodium falciparum. We've seen the prevalence nationwide, and that's across the entire country of Papua New Guinea, come down from 13% to just over 6%. So we have had roughly a 50% reduction in the prevalence of malaria. Unfortunately, we have made very little impact on Vivax malaria. And now even in highly endemic Papua New Guinea, Vivax malaria is now just a little bit more common than falciparum malaria in most parts. And all this work here I'm showing is work that's done together with my colleagues from the Papua New Guinea Institute of Medical Research, where I spent 10 years of my research life working there. What we also see with the nets, what you see here is 3 different health centers in 3 different parts of Papua New Guinea. This is before the bed nets went in, and this is 12 months after. The first what you see here is how many people have a bed net. And you see after you distribute bed nets, you hand them out, a lot more people have bed nets. But what is really impressive is this is the number of people that come to the health center with a fever that test positive for malaria. That's gone down from 70% to 20% in this area. That's really highly endemic, and has gone down even more dramatic in these 2 areas where before half the fevers were malaria, and now just around 10 to 15% of fevers are malaria. And that's 1 year after the bed nets has gone out, and that trend is continuing. So it's not all black about Papua New Guinea. We're not at the elimination stage, clearly not, but we have made dramatic improvements. And the reason why we have this improvement is shown here, and please note that this is logarithmic. So before bed nets in this one area that is striking here, extremely highly endemic, people received 300 to 400 bites of mosquitoes that carry malaria parasites per year. That was the average, 300 to 400 infected bites. After bed nets, they receive less than 10. So this distribution of bed nets has reduced the number of bites they received, and therefore where they can get infected, by over 95%. So what are the challenges? That it's not all easy. It's going to be really difficult to do. The most important thing is these countries have weak health systems. And if we have health systems that are not strong and resilient, and they have problems already delivering just curative services, it's very difficult to mount a big program to try to eliminate malaria. And we really have to strengthen health systems. We have to also get better at managing malaria cases. We need to assure that we have good diagnosis. And that's the main reason why we have problems with Plasmodium vivax, because it can hide in the liver, and we can kill the parasite out in the blood, but we don't clear all the parasite from the person, and it can come back. And that's why we need to have much better ways of attacking these hidden parasites. Lastly, these 2 points is we need to also get better, make sure that the vector control works, that people use these bed nets properly. And also, not everybody gets bitten when they are sleeping. People get bitten in the evening when they're outside and running around. So how do we control mosquitoes that bite outdoor and early in the evening? And in the Solomon Islands, these mosquito knouws are the majority of mosquitoes. The last, and that's an important kind of public health message for policymakers and funders, including countries like Australia that support this endeavor, how can we sustain public commitment and funding for malaria elimination at a time when malaria really isn't terribly important any longer, because there are only 100 or 200 cases in Vanuatu? So how do we keep that funding going? So lastly, I just wanted to say a few things about what we are doing here in our labs on elimination research. So we're doing research and trying to understand how these control activities interact in the host vector parasite interactions in our regions. We have studies to look at what these hidden stages, which we call relapses of vivax, what they do to the burden of malaria and how we can improve their diagnosis and treatment. We do studies of malaria transmission not only in our regions but also in Thailand and in Brazil. We develop novel molecular and serological markers of transmission to find out where transmission is. We have new methods that we're developing to decide where did the parasite come from. If somebody gets infected, did they catch it here locally, or did they bring it in from somewhere outside? So we're using molecular methods to show that. And also very important for me, all this basic research is really important. But if we can't support the people and programs at the front line that try to eliminate malaria, we're really going to have a problem getting the impact. So we have studies, very, very applied studies, that help the malaria control programs in Solomon Islands, Vanuatu, and PNG with their control and elimination programs. So as a conclusion, I would say technically it's feasible. Challenges remain, and really very, particularly in Papua New Guinea, and really very importantly, we have to understand this. Even though we have made this great progress, continued research on new tools and new approaches will be absolutely essential for success. That's the problem that was made in the last elimination program, that research was neglected and people ran out of tools. So as we say in the Pacific, thank you, Drew, for your attention. And that's my little story about malaria elimination in our region.
Thank you very much, Ivo, and lovely, amongst other things, an introduction to the social sciences associated with a challenge such as this. It's not just a technological fix that we need, there's this whole other aspect which Ivo was referring to. Now, to bring it all together and to continue on that global scale, Graham Brown will wrap up the proceedings and then we'll move into the question and answer session. Graham.
Thank you very much, Graham. Now, being the last speaker, I should find out a bit about my audience. How many have travelled to a malarious country? Put your hand up. Great. How many have had to have anti-malarial pills? All right. Keep your hand up. Keep your hand up. How many of you know why you had to take them for a few weeks after you came home? Be honest. Okay. Well, you've had a lecture on it and you didn't get it, did you? How many are trying to pass honours biology at school? Yeah, all right. I'll try and help you lot most of all. Okay. So we've all got our reasons for coming to this talk, and I'm going to try and put it together a little bit. The things that are important for you to remember. This is an interaction of a mosquito, a parasite, and a human population in an environment. So if we got complete dryness, you can't have mosquitoes, you won't have malaria. So it's all an interaction of these three forces actually working together. And this female mosquito must have a meal of blood in order to lay her eggs. That's why when you're camping in Victoria, that mosquito buzzes and will not stop till it's bitten you. And you can see there that she's full of blood, because in there she's taking the blood so she can lay the eggs. And the Anopheles mosquitoes, what they do, the next thing they do, they look for the nearest wall, here or here, and rest, exhausted. So that's why you spray walls of houses, because that's where the mosquitoes sit, and they eat the insecticide and they drop dead. Ivo made a point in the last one. What would happen if the mosquito had a meal and said, I'm going out the door? And there they'd be right, they'd rest in the tree and your insecticide wouldn't work. So what happens, as he said, in some places, more and more of those mosquitoes are biting outdoors. So you can spray the walls as much as you like, but it doesn't do much good. So that's an example of trying to understand that biology. Then after a period that we remember from that beautiful film from Drew, that the parasites went to the liver. And after they're in the liver, now that's the answer why you take your drugs for a longer time, because the drugs work on the form in the blood that we saw. So if you got a bite on the last day, if you're in Papua New Guinea or in Lombok or somewhere, it could take 4 weeks until the parasites reach the blood, and that's where the drugs work. That's why you're advised to take them for a longer period afterwards, because that's where most drugs work. Now, when kids get some immunity from their mother, and so they normally get mild illness, and they get lots and lots of attacks before they become, so they're not sick. So kids up where Evo works, probably before, when there was not much control, by the time they're 3 to 5 or so, they don't get much malaria. Interestingly, if you looked in their blood, you might find malaria. So they live along with the infection. A bit like probably a third of the people in this audience have had cold sores. And it comes and goes, doesn't it? You've got some immunity that controls it, but then it pops up. And that can happen with malaria. And sometimes malaria does something absolutely dreadful. And this child's got that terrible form of cerebral malaria. It's an African child with cerebral malaria. And the reason a child gets, or anyone gets cerebral malaria, well, sometimes what happens is that you remember that the parasite goes into the red cells that Wai Hong showed you, and let's say that's the edge of the red cell. The parasite puts molecules onto the surface that causes that infected red blood cell with the malaria inside it to stick. And if it sticks in your brain, it can cause this cerebral malaria that you've seen in that child there. If it sticks in the placenta, it makes the mother extraordinarily sick and has had very bad effects both for her and for her child. So malaria can cause disease in different parts of the body for people of different ages. So that really is the challenge for us when we're dealing with malaria. It's really lots of different diseases. You can be very sick with malaria with a very small number of parasites, and you can have large numbers and not be too sick as you generate your immunity. And the next slide was going to show you how the The situation had improved so much in the past 5 or 10 years. From the gloom and doom days that we, as Louis said, we'd say 5 to 10 years ago, we'd say about 2 million children die per year. That number's come down and down and down, which is simply marvellous, such that we believe there's probably now about 700 deaths per year, which is an extraordinary achievement. And that achievement is due to input from many people, stimulated by the Bill and Melinda Gates Foundation. And there, as I've said, here you can see these infected cells in the brain. But here's the wonderful changes that have happened. Look at the colour on the map, and dark is bad, and this is the number of cases. And look what's happened between 2000, where I start, and 2010. You can see how it's getting lighter and lighter and lighter, which is absolutely fantastic. Global achievement. So it's not all gloom and doom, but there's a long way to go. And why has it worked? The spraying of the walls of the houses I've mentioned, so mosquitoes feed and then go and rest on the wall, and they ingest the insecticide and they die. The other thing is bed nets, which are very, very important. Really important point as made by Evo for any intervention. If 80% of people have a net, but only half of them use it, you have to multiply 80 by half to get it 40%. So you go down and down with each of these interventions. Having a net is simply not enough. This is the spray teams at work in our area in the Pacific. Hard work to be done, very expensive. And of course, many people are concerned about toxicity from DDT. Many people want it banned throughout the world, and there's a convention this week, and many people want to ban it. But this is a life-saving medicine when it's used in this way, compared with used vastly across acres and acres for agricultural production. So we think it's good. But because of these gains, Bill and Melinda Gates said, what? Eradicate malaria? Impossible. Impossible, everyone said. But they said it's unacceptable for a child to die of malaria. If we went with our children to the endemic areas, they would not die. And so therefore, why should we tolerate such a thing? It's morally wrong. Now, the reason that people said it wouldn't work is the history of the eradication campaign in Sri Lanka. 1946, DDT spray, and they reduced the death rate tremendously. And then it went from 3 million cases to no deaths. So they said, we've done the job, stop using DDT, and within a few years, they came back to very, very large numbers. And it failed because people thought the job was done and it was over, and also with the insecticide resistance. So just to remind you then, so that's why people were dubious as to whether it could be done. But what I've shown you is a tremendous improvement. This is a similar graph, but this looks to death rates. Once again, dark is bad, and watch what happens over the past 10 years. These are utterly amazing achievements, and if we could maintain the rate even further, we could get greater improvement. So as we've heard, that there are about 200 million cases per year. It's very variable. Estimated 660,000 deaths, mainly in Africa. And as we've heard, that most at risk live in our part of the world. So less than 1 million deaths, but a way to go. Other things bring on more malaria, actually, in development projects. This was from when Indonesian people from Java moved to Papua New Guinea on migration schemes for work. And once you build a pathway into the village, the people are exposed to these forest mosquitoes and increased rates of malaria. And the same things happens in development projects in the greater Mekong region. And why is it so? Because we have great cross-border developments, a lot of economic gateway developments with people migrating across these regions. So there's tremendous importance about having a regional control program as an international public good. We've already seen this from Evo. And then if you look, what have we got? You've heard from me the stories and from others. We've got nets, spraying, proper treatment, better management, and this idea every person should be tested, everyone treated appropriately, and then track those cases. And a lot of that depends on having a system that works. Because here, of course, if there's an infectious disease, we notify it, we fix it, and we get on and do something about it. But as an example about the bed nets, if only 80% have them and half use them, that gets down. But an effective drug can be 95% effective. But if only 70% go to the clinic and only half the time is it in stock and only a third of the time does the person take the actual drugs to the course, it ends up a 95% effective drug. When you actually go out and use it, it's probably 10% of people are appropriately treated. These are problems in our health system which are incredibly hard to address. There's another enormous problem that has arisen. We've heard about the most important drug, artemisinin, mentioned I think by at least 2 of the speakers. And as in previous decades, drug resistance has first been seen in our very part of the world. And it's terribly upsetting to think, often on the border countries here, this resistance to artemisinin has occurred, such as a recommendation that combination therapy should be used at all time. But sometimes manufacturers sell monotherapy, which doesn't work properly, fake drugs are sold, and when you have inadequate treatment of anything, this is just the time that breeds resistance. So if artemisinin doesn't work, there's not much that can follow. So we're extremely worried about this, and the Australian aid agencies put a lot of money. The Global Fund for AIDS, TB and Malaria has done the same thing. It's bad enough here, but if the resistance actually spreads to Africa, it would be disastrous. There are various things happening to try and improve that. Public-private partnerships, once again the Gates Foundation and others, have been extraordinarily important in stimulating the development of new drugs in the not-for-profit sector. Now, how does it all work together? It's very interesting, but on the board of Rollback Malaria, the partnership which is trying to deliver this across the world. And there are many, many players. Just have a look at this. So that in the partnership we have foundations, mentioned up here, such as the Bill and Melinda Gates Foundation or Clinton Foundation, representative from 107 malaria endemic countries. We have donors, and I'm pleased to see that AusAid is one of those. We have multilateral agencies. I won't go, non-government organisations. We would have heard of perhaps World Vision activities, AMREF, many others are active in the private sector contributing, other members, and research and academia. Getting all these people to work together can be quite a challenge. But there is a global malaria action plan to which all have signed up to get to this end game, maintain our gains and keep them going. And therefore we say, with what we know, we can do an awful lot. The big challenge in Africa, because we believe you'd almost have to get rid of 99% of the mosquitoes to impact there. And that's why people like Louis, and we would all agree if we could have an effective vaccine, that would be a tremendous weapon in order to do what we want to do, scale up for control, sustain control, and finally elimination for malaria. Undoubtedly elimination from regions. It's already happened and will happen in other places. And let's all remember what our goal is, freedom from malaria for mothers and children. Thank you very much. Look at the time.
Thank you very much, Graham. That was a lovely wrap-up. Now it's time for the Q&A, and I realise that as a chairman I've failed you. We've only left 5 minutes, but in fact I've been given the nod that we can maybe 10 minutes, 10 or 15 minutes for discussion, questions, commentary of the panel, and then we'll adjourn and we'll finish the whole proceedings at 8 o'clock this evening. Okay, who's going to... we do have microphones, so if you wouldn't mind just indicating a question to any of the panel or the panel en bloc, or a general comment on what you've heard in this session. So, Dan, Medicines for Malaria, MMV.
Question for Dr. Schofield. The vaccine work you're talking about sounds though it's mainly for therapeutic as distinct from prophylactic application. Can you comment on where you think overall vaccine research is across the two for malaria?
That's a good question. I think the emphasis in my talk was on the therapeutic aspect because that reflects the history of that particular candidate. Namely, it was first developed as an antitoxic vaccine, but the more recent data that has sort of revivified and made that a stronger candidate is that it actually has prophylactic action, or at least we believe that it may certainly reduce the blood stage infection, but also block transmissions of mosquito. So possibly not block the infection as such. We don't really know that yet. We're looking at that. but it certainly has a wider range of activity and could be more applicable than simply a therapeutic approach. More generally, of course, the community as a whole is looking at all these aspects, but it is very challenging.
Graham?
Thank you, Dan.
Graham?
Sorry, Graham Brown.
Could I, on behalf of like my relatives who I talk to about, often don't really understand the difference between a vaccine and a treatment, just as that discussion there. A treatment is something like a drug that we would use to treat someone who's already sick. Like someone might have hepatitis or HIV, we treat them and they're sick. A vaccine is usually given beforehand in order so that you prevent it from getting that infection. Here we're potentially talking about something in the middle, which is a therapeutic vaccine, which might be, say for example, we're trying to get rid of someone who's got chronic cold sores, and then we gave some vaccine to get rid of that with a therapeutic vaccine for an established infection. So there's difference between prevention and curative treatment. So just that my friends don't understand it, so I'll take the liberty of explaining it.
Thanks for the clarification.
Thank you, Graham. Next question. Yes.
What sort of rates of vaccination and effectiveness of vaccines would you require to actually break the cycle, you know, given that no other changes in treatment?
That's also an excellent question. We have a concept of the basic reproductive rate. So for malaria to sustain itself at stable things, every infection has to give rise to a new one. The reality is that, of course, it's extremely infectious and can go on and infect many mosquitoes. A given case can infect many mosquitoes, but it comes to a point where there's balance in the community, depending on the density of the mosquitoes, how heavily infected they are. You really have to achieve. It depends how much malaria is in the community. In areas where very high transmission, such as Papua New Guinea and Africa, you really have to achieve, very high levels of coverage and efficacy in order to make an impact. But where malaria levels are already falling due to application of drugs and insecticides, a vaccine may be efficacious and a useful public health tool without achieving quite as much efficacy as that.
So to follow up on this, and particularly I think for Plasmodium falciparum, we have very good tools to actually answer that question, because we have very good mathematical models that have been developed over the last 10 years that model Plasmodium falciparum transmission on a global scale, where we can fit different types of intervention and different mix of interventions. So we can then try to predict if we have so much bed nets and we're doing that treatment, we have that level, and then we're adding on a vaccine that has this efficacy against that blood stage or against other blood stages, we can then quite accurately predict how much of coverage do we need to achieve in order to push the parasite over the edge and get transmission to collapse. So that combination of basic research that gives us understanding of the biology, then making biologically accurate mathematical models that allow us then to predict the impact on a public health scale are really extremely powerful in us answering this. That's the good story. The bad story is that for Plasmodium vivax, which is the bigger parasite in our region, we have no of these kinds of models because there just hasn't been enough focus over the last 10 years to develop them. So we quite urgently need to establish the same set of tools for the other Plasmodium parasites so we can have that same ability to plan ahead and decide what is the target we want to hit.
Yes, thank you.
Some of you mentioned about diagnosis.
Might have to put it up.
Some of you mentioned that diagnosis is another sort of way of controlling malaria in the future. Is the traditional method still sort of the best method of doing thick and thin smears in most part of the world?
Let's say that it's one of the problems that I mentioned, that we want to test every person who's ill, treat them, and then follow the number of infected individuals. Now, at the moment, really, the gold standard, if you like, against which any new test is compared is the best microscopist with the best microscope in the best place in the world. Even with that, you can miss things, because then you can do some sort of nucleic acid detection test or a gene detection test that's very, very sensitive, that is even more accurate than the test by microscopy. So new tests are being developed. For example, now there's a finger prick test that we call the rapid diagnostic test, that in the vast majority of cases, particularly for Plasmodium falciparum, it's useful at a clinical level. But if we're at the stage that we're trying to get rid of all malaria, where rather than looking at sick people, we want to know how many people in this whole audience might harbour 1 or 2 parasites that could start an epidemic, we would probably suggest either you need to treat every single person, or you'd have to use one of these extremely expensive tests that is not always available, it's more time consuming and more technical. So rapid diagnostic tests are really important, but more accurate tests are sometimes required. And in practice, the rapid diagnostic test is probably better than the average microscopist in an average malaria endemic country that's extremely poor, the people living on $1.25 per day. You don't have many microscopes there.
So just also quickly to follow up, I think it's very important, as Graham says, the type of diagnostics we need depends on what we need it for. And microscopy and RDTs are perfectly fine for treating people to find out whether somebody has malaria and decide, does he need medicine or does he not need medicine? If we want to hunt down those lost parasites that transmit, they are not very good. They miss most of it. Really, they miss 80% or more of people that carry parasites. If we go and do molecular surveys, we find, depending what tests we use, we find 2 or 3 times more people, 4 times more people that are infected than what we find by microscopy. The big question is, and we don't have an answer for that, and that's what we are trying to answer with our research on transmission in these different countries, is are these people that carry these very low number of parasites, how important are they to actually sustain transmission? Because we also have to remember that we had malaria in Northern Australia, we had malaria in the southern US, and we had malaria elsewhere, and we did not have molecular diagnostics, and we still eliminated malaria. So do we really need to hunt down that last parasites, or is it enough to be able to impact globally on transmission without finding the last parasites? And that's a really important question that we hopefully be able to give an answer within the next couple of years.
So in fact,
Thank you. Sorry, go ahead.
Thank you. That was my second question, if I'm allowed, that in case of Australia or some of the other countries where it has been eradicated, is there now sort of retrospective data as to what contributed to that?
Well, it's usually been a mixture of different things. Like some of you will have read, just as Ivo said, having patients transmitted with, malaria transmitted in Australia, and we've seen airport malaria around the world, but some will have read, for example, that there are patients in Greece with malaria. Now you would imagine in Greece, for example, there's probably a winter when the mosquitoes go away, so it may not be sustained in that way. But the parasite that Ivo referred to, Plasmodium vivax, has this troublesome characteristic that can live in your liver and come some 2 or 3 years later. It's incredible, for these students interested in evolutionary biology, it's incredibly interesting to think, how could a parasite survive a Russian winter? Well, the answer is it hides in your liver. Come springtime and maybe a bit of you get a cold or a fever, out they come and the mosquitoes are there and round it goes again. A beautiful story of adaptation in, as I mentioned, the host, the parasite and the environment.
Thank you, Grant. Can I challenge some of our younger members, the students, to ask a question, the answer to which will give you a competitive edge in terms of the marks you get at the end of the year. We have a tradition in Australia of not wanting to be seen to be asking questions, which is silly. So if you feel compelled, leap up and ask. And while you're gathering your thoughts, I'll ask Wai Hong a question. We saw that parasite getting into a red cell, Wai Hong. When you give that human malaria parasite a cell from a rabbit, say, or a kangaroo, which it's not going to infect, what doesn't happen? Does it not attach? Does it not orient? Does it not penetrate? What's the critical thing which doesn't happen in an incompatible red cell?
Yeah. So I think what we talked about was this commitment and this point where the parasite actually has the apical tip reorientated, and so that's exactly when it's looking for compatible proteins to bind to. And so when it encounters blood that doesn't have some of these proteins that are present on human blood, it basically will not undergo that active process, and then it will not commit and it will not enter your red blood cells. And so it might have these sort of bumping into your blood, but it won't have that, active movement where the tip is there and it's actually committed to invasion.
I'll ask the students a question, Graham. I'll be provocative. I'll point to some.
Ask yourself. Oh, yes.
Hi. I was just wondering if there's been any research done to try and eliminate malaria in the vector before it reaches human victims?
Get it in the mosquito.
Yeah.
Okay.
Who wants to go? Why don't you go, though? We could all do it.
Well, that's a really good question. We're getting great questions from the floor. The answer to that is yes. There's ideas about ways in which you can actually, first of all, stop a human infecting a mosquito, and ways in which you can prevent the infection in the mosquito. Obviously, you can't go about and vaccinate individual mosquitoes. It's sort of, you better kill them anyway. But for instance, you can put in the bloodstream of people drugs and other agents which are carried in with the blood meal and do the job in the mosquito's gut that actually kill. Bizarrely enough, you can introduce into people with vaccines or with drugs, which when taken up in the blood meal, as the parasite undergoes its sexual replication in the mosquito, it stops it at that point. So indeed, and there's actually a lot of work, and there's other ideas like, for instance, genetically engineering mosquitoes and releasing them into the wild to compete with wild-type populations of mosquitoes, etc., releasing sterile males that will mate with females and produce non-fertile. So there's a lot of anti-vector measures and specific ways of blocking the infection in the mosquitoes. Yeah.
And it's a good example, that questions on that. Sometimes you have to really go way off target to find new ideas. And two of the more unconventional ideas in that is that a colleague of ours who works at Johns Hopkins Institute in Baltimore is trying to vaccinate people against a sugar that is found on the lining of the mosquito gut. Because he's found that antibodies to that sugar stop the parasite of being able to go through the mosquito gut and into the salivary glands and then back out again. The good thing is also that sugar, like the GPI molecule, seems to be conserved against different mosquito species. So if you can make antibodies against that sugar, you block transmission of any parasite species and not just one. Another slightly wacky idea is that we know that people or animals that have been treated with a drug that kills worms, ivermectin, if mosquitoes drink blood from that person, they die. So we could actually treat cows and livestock that are being treated in areas where we have a lot of nomadic populations. And then the mosquitoes that not only feed people, but cows, they die when they bite the cows. So we sometimes have to think out of the box.
Well, another good example that you may have read in the newspaper is about dengue fever carried by another mosquito. They found if this mosquito is infected by another organism called Wolbachia, it no longer can transmit dengue. So if you release these mosquitoes that has already been done in Queensland and now happening in Vietnam, you've got the mosquitoes, but they can't carry dengue. They're just not able to carry it. If we could do that to the anopheline mosquitoes, that would be fantastic. It's the lateral thinking approach that Ivo's mentioned.
Thank you very much for, now that you've broken the ice, the cascade of questions. I can see all those hands up. No? Yes. Great.
What are the survival rates like? And if you survive it, you still have cells hiding somewhere, and can you get it again?
Absolutely.
Yeah, so this is, you're talking about the survivors. First of all, if the survivors of malaria, if you get over malaria, you're still at risk of getting malaria again. But with respect to malaria, also, you're at risk of getting malaria from that actual infection. In my case, I went to Papua New Guinea one Christmas holidays and got malaria 18 months later. Yeah. So the parasites had been hiding in my liver and out they came. So I didn't get too sick, but they could come up again. And if you didn't have treatment, you could relapse for many, many years.
Yeah, so even after you got sick, there could still be more cells.
Definitely.
It could come back.
Yeah, definitely. That's for sure.
but not for all parasites. I mean, we've got to be clear here. Plasmodium falciparum, which is the one that kills most people, if you take your drug properly and you get treated properly, then all the parasites in your body are dead and it's never going to come back. Plasmodium vivax, which can hide in the liver, there the problem is that the normal drugs don't kill these liver parasites. We do have one drug at the moment that is available which does kill parasites in the liver, but it's not an easy drug to use. You have to take it to give it to people for 14 days. They don't feel sick, and I'm not sure how many of us here in the room are good at taking 14 days of drugs when we don't feel sick. So, but if you don't take it 14 days, it won't really work, and it can still come out. On top of that, that drug in some people that have a certain genetic mutation can have quite severe side effects. So we have very, very little that we have to kill these parasites in the livers. There are groups like MMV, Medicine for Malaria Invention, and other of these public-private partnerships are now trying to develop new medicines that we can attack these hiding parasites that sit around in the liver.
Okay, I think we have the last question. Yes, wonderful. We end on a high note.
You've alluded to some of the differences in the species of malaria, in particular hypnozoites in Plasmodium vivax. Are we oversimplifying things to consider malaria as a single disease, or should we be tailoring programs to target the specific species that exist in given countries, and how can we do that?
Okay, I think let's have all the panel give a very quick answer to that very important question.
So my response to that is it's a massive oversimplification if we just treat it. Obviously, it's a highly heterogeneous disease with all sorts of different expressions, and we need to tailor specific solutions to specific environmental conditions, et cetera, et cetera. Having said that, we should always keep our eye on the main game and try to develop tools. If we're talking about research and development for new tools, they're as broadly as applicable as possible, such as some of the vaccines that I hope that we'll be able to develop in the coming years.
So I work on the most lethal form, which is Plasmodium falciparum, and so what we look at are, how it enters blood. But some of the basic biology that exists there obviously is translated into vivax and nosei. And so I think when we think about vaccine development, although we're quite focused on one particular species, our eye really as biologists is to cover all of them. And some treatments will be across species, some will be quite narrow, and I think the thing to do is to really be very broad in the interventions. I mean, the other complicated thing too is that as Plasmodium falciparum incidence drops, sometimes Plasmodium vivax incidence rises, and so it's really important to, I think, target across.
I think the answer is absolutely. It's a total oversimplification. And I think we have started to change that view with the view of talking more about elimination and eradication. 10 years ago, malaria was identical to Plasmodium falciparum malaria in Africa, and everybody who talked about malaria thought about falciparum malaria, because that's what kills 90% of the people. So when we're talking about stopping people from dying, malaria is falciparum malaria. When we're talking about eliminating malaria, we can no longer think about that simply, because there are vivax and falciparum. Not even talking about ovale and malaria and nullsei, which people are just consider collateral damage, that they're just hoping they're going to get wiped out if we attack the other two. But very clearly, at least, falciparum and vivax will need substantially different approaches if we want to interrupt transmission. And because of that focus on very important focus on preventing deaths in Africa, a lot of the tool set that we currently have has been developed to combat African falciparum malaria.
Okay,
and we're now trying to apply it to other species.
Graham.
Yes, that I agree with what's been said. And when we were looking at the malaria eradication research agenda, some advice to Bill and Melinda Gates was just go for falciparum first, for the reasons that Ivo said, that it's a killer. But 20 years ago, after the malaria eradication campaign, everyone decided that we needed specific attacks. Forest fringe malaria isn't going to work. Bed nets, for example. Migrants and refugees, children in Africa, different from adults in PNG. But right now, there's a crisis. I showed you the improvements that's happened over the past decade, which are truly spectacular and wonderful. You probably noticed the bed net expenditure in some of the graphs from Evo. Now, a long-lasting insecticide-treated net probably lasts about 3 years, perhaps. Now is that the big injections of money came up till 2 years ago, and since the global financial crisis has come, they've fallen right down. And it's very, very unlikely that there will be replenishment of the Global Fund for AIDS, TB and malaria. A lot of the gains could be lost, and we know potentially we'll get the Sri Lankan situation replicated, we hope on a minor scale. So governments of Africa are having to say, we've got restricted budget, do we do spraying, do we do nets, do we do drugs, do we do it just here, just there? So they need to have this decision. Now, we only need $6 billion a year for what's been achieved, and even that wasn't enough. You could laugh. We spend I was told in national radio, $20 billion per year for air conditioning for troops in Iraq and Afghanistan. Consider the trillions that we spent to rescue the banks. Consider the annual profits of the great mining companies. At a global scale, $6 billion is tiny, and each and every citizen should be saying that and encouraging our governments to make the contribution to save the lives of what could be another Shakespeare or a Mandela. We know how we can save lives, but we need to each to make that commitment to try and maintain the gains.
That's a very good rallying call to end on, Graham. Thank you. And thank you for that question. I think the students of infectious disease understand it's the specifics, it's the detail, it's that deep knowledge which one requires, and I think you will have seen some of that deep knowledge on the stage this evening. Can I just remind you as our guests to pay attention to this feedback, which is always important in WeHi lifting its game and giving you more quality product. If you could fill out this questionnaire, much appreciated. Thank you very much for your attendance.